The last topic that we have on Aldol reactions is something called an intramolecular Aldol reaction. Could be just an addition, or it could be addition followed by the condensation. Intramolecular means within itself, within a single molecule. So an intramolecular aldol reaction is when you have a dicarbonyl. What does that mean? That means that you have a molecule that has two carbonyl groups, two carbon-oxygen double bonds. So it could be a dialdehyde, or it could be a diketone, or it could be a molecule that has an aldehyde and a ketone. A dicarbonyl in an intramolecular aldol reaction, the dicarbonyl reacts with itself doing an aldol reaction, and it produces a ring. This reaction only works when the product is a 5-membered ring or a 6-membered ring. To produce a form, to produce a 5 or 6-membered ring. You have probably seen enough organic chemistry in your life to know that 5 and 6-membered rings are the most common sized rings. And that is because the bond angles in a 5-membered ring and a 6-membered ring are the closest to the ideal or normal bond angle for an sp3 atom, which would be 109.5. If you have anything larger or smaller than a 5 or 6-membered ring, the bond angle gets too far outside of the normal angle, the ideal angle, that the steric hindrance and the strain and stuff like that becomes too great. So although you've seen plenty of smaller rings or larger rings, the 5 and 6-membered are the most stable rings, and this reaction is just not pushy enough to make a ring that is smaller or bigger than 5 or 6-membered. So let's take a look at how this reaction works. Back to our worksheet. So here is an example of a molecule that's going to do intramolecular aldol. And we want to draw all the possible products. So when we're asked for all the possible products, it means only the 5 or 6-membered rings. So, of course, on paper you can make any size ring you want, but in reality, the possible products are the ones that would be 5 or 6-membered rings. So when you're doing an intramolecular aldol reaction, you have to consider the possibility that either that carbonyl is going to attack that carbonyl, or the other way around, this one's going to attack this one. It's kind of like a crossed aldol reaction, but it's just all in itself. So the first thing that you want to do is identify all of the alpha hydrogen, every single one of them. And I'm going to draw them all in. All of these alpha hydrogens are removable, and therefore they are all potential sites where the molecule can become an enolate and positions where attacking can come from. Is this an alpha hydrogen? No. That is not an alpha hydrogen. That's a hydrogen straight on the carbonyl group. In order to be an alpha hydrogen, you have to be on an alpha carbon, not a carbonyl carbon. So these are all of our potential alpha hydrogens, and we need to consider the possibility that any one of them can be removed. So I'm just going to work through these alpha hydrogens from left to right, which means I'm going to start over here, grabbing that guy, and that means I'm going to be making the first enolate that I make is going to look like this guy right here. So I've stopped drawing the alpha hydrogens because it's not important anymore. Once I've made that first enolate, this negatively charged carbon is going to attack a carbonyl carbon, and of course it does not make sense for it to attack that. That's not, they're too close together. There's no way you're going to make a ring like that. So this is going to attack that carbonyl group right there and open that bond up. And if we did that sort of attack, what would this molecule look like? Well, I always want to encourage you to just draw these molecules as ugly as you need to draw them in order to make sure you're not losing any carbons. Plus, just like with regular aldol reactions, we want to number our carbons again to make sure that we're not losing any of them. So I'm going to draw this super ugly because I don't even care right now what it looks like. 1, 2, 3, 4, 5, 6, 7. When I attacked, the oxygen opened up to become an O-, and I created a bond in between carbons 2 and 6. That's really ugly, but I don't care because I know I've connected the atoms correctly. So now I want to make this look better. I'm also going to protonate while I'm at it. Let's protonate that oxygen. Let's do that part. And let's redraw this and see what it looks like. We're going to make it look good and protonate all at the same time. So this 2, 3, 4, 5, 6, that's a ring now. And how many carbon atoms are in that ring? 1, 2, 3, 4. 1, 2, 3, 4, 5. So that's a good ring. 1, 2, 3, 4, 5. Number it because numbering is going to help us get everything in the right spot. 2, 3, let me draw that bigger so easier to see. So let's number it. 2, 3, 4, 5, 6. And then just like we did with the other aldol reactions, now let's start filling in. What do we need to fill in? So on carbon number 2, we have carbon number 1, which was part of an aldehyde right there. And on carbon number 6, we have our OH. So there it is. That's the addition. Whenever possible, we always want to go all the way through to condensation. So let's remember how to do that. To do that, we need to find the OH carbon, and we need to go towards the aldehyde to the adjacent carbon. Is there a hydrogen on that adjacent carbon? Yes, there is. Since there is, that means that we can do condensation. And I'm going to draw this condensation all in one big step. Grab the hydrogen, move the carbon-hydrogen electrons down to make a double bond in between 2 and 6 and get rid of the leaving group. And so that leaves us with this. That wasn't a great double bond. This beautiful conjugated molecule. So there's one of our products right there. That was just one. That came from removing one of these alpha hydrogens. So let's continue down with this dicarbonyl. I'm going to redraw it. I'm going to put the alpha hydrogens back on. We're not going to mess with these two guys because we've already tried them and they worked well. So now we're going to consider what if we grabbed with the hydroxide the next set of alpha hydrogens down the chain. So these guys right here. And we formed that enolate right there. So let's draw what that enolate would look like. Negative charge on that guy right there. So now we want to ask ourselves, who is that enolate going to attack? Well, that enolate cannot attack its own carbonyl carbon. That's too close. So the enolate is going to need to attack out here and open up carbon-oxygen bond like that. And let's see what that would get us. So the first thing I'm going to do is draw it out real ugly. So I'm not going to worry about, is this going to look good? It's just going to look bad, and I'm okay with it looking bad. How am I going to draw this? Boom. There's the bond that I made. Let's put some numbers on those carbons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And let's protonate our O-, and let's also simultaneously see if we have a good looking ring. So we're going to protonate the O-, and then we're going to see what kind of ring do we have? How many carbons do we have? We have 1, 2, 3, 4, 5. So that's a good looking ring. 5 or 6 membered rings are good rings. Let's draw that ring out. Let's number it. 1, 2, 3, 4, 5. And what do we have on carbon number 1? On carbon number 1, we have an OH. We also have a hydrogen. We can go ahead and draw that in. And then on carbon number 5, we have 6 and 7. Like that. So we're going to ask ourselves, can we dehydrate? Can this thing react even further? Can we do the condensation reaction? So we've got to find our OH, that's on carbon number 1. We need to make a double bond towards the carbonyl group. So that means we would like to make a double bond to that spot. Does carbon number 5 have a hydrogen on it? Yes, it does. So that means that we can do condensation. We're going to grab the hydrogen off of carbon number 5. We are going to move the carbon-hydrogen electrons in to make a double bond between 1 and 5 and get rid of the OH group. And this product looks like that. Another conjugated 5-membered ring. So that's good. We have one more possibility. So for this reaction, second time around, we considered this guy. So far we've looked at 2 of the 3 sets of the alpha hydrogen. We have one more set of alpha hydrogen to consider. So I'm going to redraw. I'm only going to draw in this last set of alpha hydrogen this time because we're not doing anything with the other 2. I already know that. So we have our hydroxide, and the hydroxide is going to grab one of these alpha hydrogens, and it's going to move the carbon-hydrogen electrons onto its own carbon to make the enolate. So let's draw the structure of that enolate. It's going to look like that. And where will the enolate attack? It can't attack like that. That's too close. So that means the enolate needs to attack here and open up that carbon-oxygen double bond. And let's see what we get when we do that. I'm going to number the carbons first. 1, 2, 3, 4, 5, 6, 7. And let's redraw O minus 1, 2, 3, 4, 5, 6, 7. And we bonded 1, 2, 3, 4, 5, 6, 7. We made a bond from 7 to 1. So let's see what we can do with that. So let's consider reprotonating our oxygen and redrawing this molecule looking nice. And how many carbon atoms are in this ring? 1, 2, 3, 4, 5, 6, 7, which is not 5 or 6, which means that this reaction actually doesn't work. It will not happen. And we kind of have to get almost all the way to the end of the mechanism before we figure that out. It's not going to get to this part and stop. It's actually going to stop like right here. No reaction. All of this stuff that we draw is not going to happen. No reaction.